The following question reads that the combination of mass spectroscopy and NMR spectroscopy provides a powerful method of analysis of organic compounds. And the mass spectrum of compound G contains M+1 peaks in the ratio of their heights, which is given as 74 ratio 2.5. And you're supposed to use these data to calculate the number of carbon atoms present in G. Show your working. Now remember, when you're doing mass spectrum, there's a molecular ion peak, and then there's an M+1 peak, which is because of carbon-13 isotopes. So if you have a carbon-13 isotope, the mass of the molecular ion would increase by 1. So the ratio of M+1 is going to give you the total number of carbon atoms using the formula. The number of carbon atoms is going to be 100 over 1.1 multiplied by the M+1 height, and M, the ratio of M+1 to M, which in this particular case is 2.5 ratio 74. So if you calculate this, and if I multiply 100 over 1.1 into 2.5 divided by 74, the answer that I'm going to get is, on my calculator, it's coming out to be 3 carbon atoms. So it's coming out to be 3 carbon atoms. So my molecule has 3 carbon atoms. And let's move to the next part, which is the NMR spectrum. So that's the first information that's given. I don't think there's any other information that could be extracted from the information provided. We just know that there are 3 carbon atoms. Now moving to the next part of the question states that the NMR spectrum of compound G is shown. So this is the NMR spectrum of compound G, and you would notice that there are 3 chemical environments. First thing that you will notice, there are 3 chemical environments. One is this one, then you have this one, and then there's a third chemical environment at around chemical shift 12. So 3 chemical environments are given. And the other thing that's given is the peak splitting. This one, the first one is a singlet peak. This one over here is a quadruplet peak. If you look carefully, there are 4 peaks. The peak has been split into 4 sub-peaks, so it's a quadruplet peak. And this one over here is a triplet peak. What information does that give us? A triplet peak is going to indicate that the neighboring carbon atom over here, the neighboring carbon atom is going to have, it's going to have 2 hydrogens. So that is the information that is provided by a triplet peak according to the N+1 rule. Similarly, you have a quadruplet peak that indicates according to the N+1 rule, and that indicates that the neighboring carbon has 3 hydrogens. And a singlet peak is usually obtained when the neighboring carbon atom has no hydrogens at all. So neighboring carbon has no hydrogen, or it could be an OH peak or an NH2 peak. Or the third option is that the neighboring carbon has no hydrogens. So the peak splitting would indicate what the neighborhood would look like. Now, if a neighboring carbon atom has 2 hydrogens, that indicate that the atom next to it is probably CH2. Only then the neighboring carbon atom has 2 hydrogens. And similarly, if the neighboring carbon atom has 3 hydrogens, and it's giving you a quadruplet peak, that would indicate that the neighboring carbon atom is probably CH3. The neighboring carbon atom has 3 hydrogens. So what these 2 peaks would indicate is that whatever the protons in these 2 peaks are, this one has CH2 as a neighborhood, this one has CH3 as a neighborhood, which would indicate that CH3 and CH2 must be together. Because one of the protons, they're telling us that the neighborhood has CH2. The other one is telling us that the neighborhood has CH3. The only way the 2 have each other as neighbors is they're probably together with each other. So I pretty much figured out what 2 of the protons would look like. There's a CH3 peak, and then there's a CH2 peak, and this splitting, this one is a triplet peak, this one is a quadruplet peak. And I'm also going to draw arrows just to show that this over here would probably be a triplet peak, so it's probably this one over here, and this one is going to be a quadruplet peak because the neighborhood over here has a CH3 group, so it would be split into 4 peaks. Now, I also had a third carbon atom, which is over here. This carbon atom also has protons, and it's resonating at around 12. So let's go and look at the data booklet and see at what chemical shift do we get protons that resonate at around 12. So I've taken a portion of the data booklet, and just to show you that if you look at the OH bond, and if you look at the chemical shift, there could be many different OH, these hydrogens, these protons. If you look at the proton in OH, the hydrogen in OH, you will notice that there are many different protons that have OH. It could be a normal alcohol, it could be a phenol, which would be next to benzene, or it could be an OH, a proton in carboxylic acid. Now, our peak was at around 12, so the only proton that comes within that range is this carboxylic acid proton, this OH proton. So that means the carboxylic acid group must be present in the molecule. So let's go back to our question, and let's focus on this last peak, singlet peak that we had at 12. Remember, OH peaks don't split. They're always singlet peaks. NH2 is also always singlet. So this must be a COOH group. The proton must belong to carboxylic acid. So now to complete my molecule, I had a third carbon atom. I'm going to draw a carboxylic acid having this final proton, which is the OH proton in carboxylic acid. So this is the chemical shift. This is the one that's resonating at chemical shift 12, right at the end. So I figured out by looking at the NMR spectrum, I figured out what molecule this must be. There were 3 carbon atoms. Triplet peak indicates that the neighboring carbon atom has 2 hydrogens. Then there was another peak, a quadruplet peak, that indicates that the neighboring carbon atom has 3 hydrogens. And then I had a peak at around 12, that indicates that there must be a hydrogen in carboxylic acid. Now, in the next part, what I just need to do is I just need to fill the table. I've already figured out everything about this question. First thing, that is the chemical shift at 1.1. So at 1.1, it's this CH3 peak in the alkyl chain. So let me, what I'm going to do is I'm going to answer this question in a way that I'm going to underline. It's going to be this CH3 next to alkyl. Then this 2.2 is this quadruplet peak over here because of CH2. You can also confirm this. It's resonating at 2.2. CH2 next to serial bond O. Let's see whether it resonates if these protons resonate at 2.2 or not. So I've opened the data booklet again, and remember I had this hydrogen CH carbon chain protons, and if they're next to serial bond O, they would resonate at 2.2 to 3, which is exactly what we have in our case as well. So going back to my question. So this at 2.2 or 2.3 is CH2 next to serial bond O. So let's write this down. It's CH2 next to C double bond O. And the last one at 11.8, that's the one because of carboxylic acid. So it's C because of COOH proton. So I filled the table, and in the next part, you're being asked the addition of D2O causes one of these absorptions to disappear. Explain why this happens and state which absorptions is affected. Now, first thing is, what is D2O? Now, when you talk about D2O, D is basically an isotope. It's deuterium. It's an isotope. And the isotope has an even number of nucleons. If it has even number of nucleons, that basically means that it's not going to have any resonance, no resonance. Now, this deuterium isotope, because both spins are going to be paired, two nucleons having paired spins, the net effect would be it's not going to have any overall magnetic spin. No magnetic dipoles would be created. Now, coming back to our question, remember always that this 11.8 peak is going to disappear. Reason it's going to disappear is because carboxylic acid dissociates. And this proton, if it dissociates and breaks down into ions, it becomes part of a reversible reaction where the carboxylic acid group would be dissociating, it would be leaving its H+1 ions, and in the reverse step, they would be joining back again. But if the water contains a lot of deuterium D2O, there would be a lot of D+1 ions. So in the reverse step, when the reverse step happens, there are chances that instead of forming RCOOH, you might get RCOO minus 1, and D might get joined or get replaced. The H would be replaced by its other isotope, which is deuterium, and this would not resonate. So your carboxylic acid peak, which was at 11.8, would disappear because the carboxylic acid H would be displaced and replaced by the other isotope, which would be coming from D2O or heavy water, and it's going to displace that, and it's not going to resonate any longer. So 11.8 peak would disappear. And the answer that you're going to write is that the carboxylic acid 11.8 peak disappears, and because H gets replaced by D, which does not resonate. In the next part of the question, you're being asked to draw the structural formula of G, which we have already figured out. So let's move to the next part. The next part is that there's several structural isomers of G that exist, and you're supposed to draw the structural formula of an isomer of G with only two absorptions in its NMR spectrum. What two absorptions indicate is that there are going to be only two chemical environments. So let's have a look at G, and I'm going to try and figure out. Now G has three chemical environments. These three hydrogens are going to resonate at a different frequency chemical shift. These two hydrogens are going to resonate at a different chemical shift, and this hydrogen is different amount of shielding, so it's going to resonate at a different chemical environment. So I'm going to draw an isomer of G that is only going to have two absorptions. And since this is a carboxylic acid, the only thing I can do when I'm drawing isomers is I can make an ester. So there's going to be serial bond O in the middle, and there's going to be two CH3, one CH3 on the right side and one CH3 on the left side. Now this is an isomer, and you can pretty much notice that there are only two chemical environments in this molecule. There's these protons and there are protons over here. They're going to resonate at different frequencies because these protons are bonded to single oxygen and these protons are bonded to C double bond O. So the chemical environments of these two protons are going to be different. So if these protons resonate at frequency F0, these protons would resonate at frequency F1. So two different chemical environments, two different chemical shifts, two different frequencies would be absorbed from the radio waves. So draw the structural isomer of G with only two absorptions. So we have done this. The answer is written over here. And moving to the last part, which is use the data booklet to suggest where these absorptions would occur. So we have our CH3s. One of these protons are next to serial bond O, the other protons are next to single O. So let's open the data booklet. Here's my data booklet, and I've highlighted the CH bonds. If they're next to serial bond O, they're going to resonate at around 2.2 to 3. Whereas if they are next to single O, as shown over here, then they're going to resonate at 3.2 to 4. So let's pick a value. Let's resonate these at 2.3 and these at 3.3. And go back to our question and answer the question. So one peak is at 2.3, whereas the other one is at 3.3 chemical shift. And I'm also going to write down which peaks. This one was CH3 next to, although this is not required, serial bond O, and this other one was CH3 next to single O. So these two protons, this one resonates at 2.3, this one resonates at 3.3. As you can see in this molecule over here, two different environments. This one resonating at around 3.3, 3.2 to 4 was the correct range. This one was resonating at 2.2 to 3, so I took it as 2.2. Let's call it 2.2 then.